Beh, però già questo è buono. Ok.
Recording in progress.
Good lunch, everybody. I should say good afternoon. Technically, it's just started. And welcome to this Quantum Seminar. Today, I have the great pleasure of welcoming Nathan Shammah here at PFL. And let me say a few words about Nathan. Nathan did his PhD at the University of Southampton under the direction of Simone De Liberato, and then he joined RIKEN in Japan as a postdoctoral fellow, and he already started showing his taste for the management of research, not only the research in itself, but also the management, because he is the vice president of the Association of Italian Researchers in Japan. So just the first step of a brilliant career. Today, Nathan is the CTO, the Chief Technology Officer of the Unitary Fund, and he will tell us, I hope, about the Unitary Fund, and also the Managing Director of the Unitary Fund France. And he works as a researcher, but also as in this great challenge, which is the management and encouragement of research. So I'm looking very much forward to your talk. Today we'll be talking about error correction in quantum computers with open source tools. Thank you very much.
Thank you, Professor Savona. Thank you to all of you, the organizers, Fabrizio Minganti, everyone for being here. It's a great pleasure. And today I will speak about benchmarking, simulating, and correcting errors in quantum computers with open source tools. And this is the outline of the talk. I will first give a brief outline of...
Recording in progress.
Yeah, great. I will give an outline of Unitary Fund, what it is, what we do, what are the microgrants, what are the hackathons we do, and the other programs we are involved in. But then, of course, I will focus on research and tell you a bit more about some of the projects we are supporting and developing in-house with a broad community. So, let me start very broadly. You may recognize all of these symbols. Linux, the Wikipedia symbol, and archive. And these are three examples of great open source projects that advance our knowledge and also enable us researchers to work more effectively in the spirit of open knowledge and open science. And all these projects have some foundations that are supporting the development of the projects themselves. And they do it for the benefit of wider society, contributing, for example, as in this estimate by the Linux Foundation, over 5 billion in contributed development cost for software development at large. So that's really how Unitary Fund got started and why it was funded, in order to support this open source environment and more broadly make quantum technologies as open as possible. And actually really excited, it was the inauguration of the Open Quantum Institute here in Switzerland the other day, and I feel that this spirit should be encouraged further. But let me tell you a bit more practically what we do. Because of course, we're not at the level where we have something like a Linux operating system or a quantum computer. There are many challenges. And so our approach is not exactly that of a Linux Foundation, although maybe some days in the future it will be that one. So this is a graph that is showing what we could see as like 3 stages of open source in quantum technology, what one could call academic prehistory, starting with QTIP around 2011, an intentional openness of the industry, of course the IBM quantum experience, the Qiskit ecosystem, and then today's open environment that is full of open source projects, in some cases which address specific niches. So today's environment is intentionally open, and I think it's important that as the development of these technologies keep upgrading and advancing, we keep an eye for this pre-competitive stage. So there's a lot of national security strategy discussions around the development of quantum technologies, but we really need to keep this environment open because simply there is a lot to discover. And open source, it's a way to do research at scale, develop tools that other researchers will use. So there's a lot to build in quantum hardware and quantum software, and we cannot every time reinvent the wheel. So I was saying that how the Unitary Fund got started. This is like a very brief introduction. It really got started with a bit of frustration from the academic sector where there is a lot of bureaucracy when applying to grants. And these were really small grants, we call them micro grants, started $2,000, now they're $4,000. No strings attached, everyone can apply, everyone in this room, by the way, there is no affiliation required. And we've so far funded more than 90 teams across 26 countries. And this led to a broad wealth of publications, software being developed, in some cases even startups being funded. But again, let me focus here. This is not like technology transfer for startup creation. This is something a bit different. This is like project validation of an idea. I will give some examples. At the same time, to also make the ecosystem more efficient, we need to sort of put together forces and have folks work on specific projects without too much duplication. And in some cases, Unitary Fund is specifically well positioned as an independent player to build these open source tools. So I will speak a bit about Mythic and Metric in the rest of the talk. But before getting into that part, that is more like the research-oriented part, I will also give an overview of the community programs we support and we organize, and I hope you can take part too. So starting with the team first. So this is the Unitary Fund tech staff, which I lead. I will speak about work in which Andrea Mari was involved, now at University of Camerino, Misty Wall, Dan Strano, Nate Steeman, and Vincent Russo, together with William Zecht. And actually, among our alumni, there is Ryan LaRose, who was for some time also a postdoc here at EPFL, but was intern with us during his PhD. And yes, this is the board of directors. I'm really glad to be joined by Travis Schulte, Christoph Josak, and most recently, since last week, by Anastasia Gamic and Liz Durst, who previously led the IBM Quantum ecosystem. So, a bit of information about Unitary Fund. We have a broad wealth of collaborators in academia. We also have some supporters. So that's how we fund our programs, thanks to a member program that is joined by some core members, such as IBM and Scientifica, and also some other supporting members. You will see some known names among the quantum startups and quantum industry. But we also are software developers in research and development in some grants. So we're also supported by some grants by the Department of Energy, the National Science Foundation, and most recently the Wellcome League. I would especially like to thank our advisory board, which has 23 volunteer experts in quantum systems and software from a wide range of institutions globally, from South Africa to Canada to even Europe. So I will speak about the microgrants. And I want to give here a snapshot from the Unitary Fund website where you can see the 4 most recent microgrants. And I'm just going to read the titles. So the latest one has been announced. It's an entanglement toolbox for T-doped stabilizers states beyond the classical simulability barrier. So this is a very useful tool. It actually builds upon another tool that we founded, which is called the PyClifford, Py for Python, Clifford for Clifford circuits. But this is actually with T-gates inside the quantum circuits. There's another project on topological quantum error correction, which actually is spinning out of a Google collaboration. There is a project by Professor Matthias Fitzpatrick on a qubit pulse, educational qubit pulse engineering game. And there is a project that will be across France and Venezuela called Quantum Chamitas by Daphne Carolina Arias Perdomo to help develop high-quality STEM material for girls in Venezuela and France beyond, let's say, the Paris hub, which already has a lot of activity, but in other geographies. And we're starting to see some network effects among these grants. So this is an example of two projects that we funded. One is yao.jl, which is a SDK in Julia. And the other one is PyZX, which is a Python toolkit that is using ZX representations to optimize quantum circuits. So what PyZX does, takes your quantum circuit, map it to a graph, and then manipulates the graph thanks to this ZX calculus, of which I'm not an expert, but then optimizes and reduces, for example, the 2-qubit gate count. And actually, the folks at yao.jl were inspired by PyZX, and they created their domain-specific language, YaoLang, that supports ZX calculus. This is just one example of an interaction. So, if you want to join this community, I think the best thing is to join our Discord server. We have many activities weekly, almost daily on it. We have some community calls of some of these projects, and we also have an open seminar, which is very informal, called Quantum Wednesday. It happens that I'm giving the next seminar in April, but usually it's a broad range of speakers from also other institutions. Talking about other programs that we support in-house, one is Unity Hack. Does anyone know about it? Raise your hand. Only one. Okay, great. That's great. So there is a lot of hackathons nowadays, and that's great. One problem of hackathons is, though, that the proof of concept usually is trashed in the bin the day after the hackathon. They're great for talent sourcing for the industry sector, but what is important, we believe, is also to build software that is used by other researchers and developers. And that's why we designed Unity Hack, which actually goes to some well-established open source software projects and asks those maintainers what are the issues where you would like some help from the wider community. Also community of quantum enthusiasts that are not quantum researchers as you. And that's why every year now for the past 3 years, and we'll have also this spring, we run this hackathon that you can learn more about unityhack.dev. It's fully remote, and it lasts around 3 weeks. And how does it work? I'm showing here an example. Here are 3 projects, Simmer, SC Qubits, and Tokito. They do different things. Unity Fund puts a pot of money, about $500 for each project, and tells the maintainers, list the GitHub issues where you would like some help. And thanks to some automation on the website, when that issue is closed by someone in the community, the issue is closed, and the award is then given to the hacker who actually had solved the issue. So these are the stats of last year Unity Hack. About 750 hackers participated. They had solved 99 bounties, so issues, closing issues on 30 projects. And this would not be possible. Sorry.
Very silly question.
Yeah.
How do you give the money? Because this is instantaneous and remotely. So how do you transfer the money?
So you need to register and give you your, for example, bank details on the website. And once we see that there is the bounty is closed and this is confirmed by the maintainers, we wire the money. And so Unity Fund takes care of all of this. That would be very hard to do for even folks like AWS.
Sure.
So this is one example. That's completely remote and online. But recently we started hosting our first in-person events. It's called UnitariCon. It borrows from the PyCon ecosystem the name. It was held in Italy thanks to the Quantum Italia initiative. But actually, we would be very happy for this year and the following years to host more events at universities and other places. And this was really like an opportunity for the developers in this field that are working on these projects, plus some others, new ones, to meet and code together and learn more about the more finer grained updates from these projects. And finally, about the programs we run, that is not research. We've been running for 2 years the first survey on quantum software, open source quantum software. As an independent organization, it's important that this is run by someone who doesn't have vested interest in the field. And actually, I think that also for researchers, this survey, which is online and completely open source also in the data, contains very interesting information. For example, what software languages are used, programming languages are used to program quantum computers and quantum software. As you could tell, Python is very popular, but for example, as you can see here, Rust is becoming more and more popular together with other programming languages such as Julia, whereas C++ is becoming less popular. Or for example, you could learn about what cloud service providers, so we're talking about service providers that give you access to quantum simulators or hardware, are most used by the community. Or also what kind of specific tools. And finally, what needs to be built for quantum software to be successful. And the community is quite clear. You need to have a good documentation to your software project so that others can use it. So part of the support we give to these projects is also, for example, in building documentation that another can use to explore the API doc and also the user guide. Great. So this was the introduction before getting started with the research part. And today we'll speak about quantum error mitigation, benchmarking, classical simulation, and actually we'll not speak about software applications because we don't have, I don't have time. And also we'll mention open hardware, but all papers are listed on our website. So let me start how I got started into this field, which is by running some scripts in Qtip, the quantum toolbox in Python, which is a simulator for open quantum systems, to which I contributed a specific submodule that helps simulate many-body quantum systems in a dissipative local environment interaction, when there is like the interplay of a driven dissipative phenomena. And these are just some things that you can do with Qtip, which now has reached 1 million downloads. So what we did at Unitary Fund for the Qtip project, it started actually before Unitary Fund, but actually it started in the group where I was a postdoc at RIKEN, and we had set up independent governance with a board and an admin team, setting up some communication channels, and then increasing the rate at which the admins and also the board members were meeting. And now I'm really glad that later this month I will travel together with Alberto here to the second Qtip developer workshop that will happen at RIKEN this year. So of course, with these open source projects that are great, you also, especially when they're large and serving a large ecosystem of users, you also need to facilitate the communication among the developers themselves and the maintainers. In specific, one thing I had sort of like spin out from the main Qtip project is a Qtip QIP. QIP stands for Quantum Information Processing. So there are many SDKs right now to design quantum circuits that then run on actual hardware. But actually Qtip is especially well positioned to simulate any kind of backend, let's call it, or any kind of quantum hardware, thanks to the Hamiltonian and the dissipative master equation solvers it has behind it can enable behind the scenes. So what Qtip QIP is specifically good at doing is transform the quantum circuit into a pulse level ensemble of time-dependent coefficients acting on an Hamiltonian, in some cases with an open system approach, so also in a Liouvillean setting. and then simulates it on the specific simulated device of choice. It is not the only it's not the only system to do this. There are also more specific systems, sometimes embedded in with others, such as Skid Pulse, or as in the case for Pulsar and Blockade, that are focusing on specific simulators and QPUs. In these cases, Rydberg atoms, which have some specific properties, such as that the QPU every time can be reinitialized. And so, for example, for Blockade, you see there that on that grid you can place quantum atoms as you the Rydberg atoms as you wish, and then you can simulate what kind of interaction they have. So, talking about quantum circuits and getting closer to error mitigation. This is von Neumann master equation, which is just the Schrödinger equation in its master equation in its density matrix form. And when we write in the quantum circuit formalism, we're assuming that there is a noiseless time-dependent Hamiltonian that is being applied to the qubits of interest. But you know that if you add too many gates to this quantum circuit, in this case only two, an Hadamard and a CNOT, at some point what you will obtain is just white noise. And that is because quantum computers actually can be also be modeled as open quantum systems. The simplest example of which is an atom inside a cavity, which has the cavity itself and the atom some dissipation rates. And so the coherence time of your system is not infinite. So we have to fight with this, against this, and there is a very popular approach that has been developed, which is quantum error correction. But today I will speak about quantum error mitigation, which is an alternative approach that can be used on these devices nowadays. Before getting to this, let me also take a more sort of like operational point of view of what does it mean to run a quantum circuit on a simulator or hardware provider, especially now that many are connected to the cloud. So you actually send your quantum circuit, and what you get back are a number of bit strings. And here you see 0, 1, 0, 1, 1, 1, 1, 0, 0, because we assume that you have many qubits in your system. And we said that at some point, if you have too many operations on your quantum circuit, on nowadays quantum computers, what you will get in the end is just sort of like white noise. But actually, if you get before that threshold, what happens when you start to run random quantum circuits and you measure the outcome? So what you can start to count are so-called collisions that in statistics just mean when you have a bit string that is repeated in two cases. And what my colleague Andrea Mari has shown, it's very interesting, is that the higher random states have a different statistics than the uniform distribution of random variables. So when you start to count the number of collisions against the number of shots, you can actually see a difference between a uniform distribution or this Porter-Thomas distribution that is followed by these higher random states. And actually you can use this very simple benchmark, which by the way doesn't have a computational requirement that quantum volume has, to tell if your device at a given level of number shot or a given level of depth has a difference with a black box that instead is a classical device.
So it's more than quadratic, the power, the Porter-Thomas distribution. Because the uniform should be quadratic.
Yes. And of course there is an overhead in doing this. The point is that the overhead scales like 2 to the n half. So that's where you get an advantage with respect to just 2 to the n. And Andrea runs some simulation, and with alpha represents different fidelities. So alpha equal 1 is fidelity 1. You could reach in 1 minute, like you could verify quantum supremacy beyond the quantum supremacy regime with a moderate number of shots. Actually, if you decrease the fidelity of your system, we're showing that, okay, we're not yet there to use broadly this method, but if we assume some development in current NIST devices, this will be in the order of like days if you assume a realistic number of shots for your benchmark. So, and last project I'm going to speak about is QREC, which is a C++ project which is fully empowered by GPU access and lower level optimization. And QREC is actually a simulator that simulates quantum circuits in an exact or approximate way. So what you see in these two graphs is a benchmarking of QREC with other simulators that are available, and also quite interesting with a fast Fourier transform that is completely classical. It has nothing to do with a quantum system, pi FFTW. And you see that QREC has a competing capabilities, also especially for moderate number of circuit depth and width. And also we are simulating, we already obtained some preliminary results simulating up to 54 qubits, approximately, of course, getting close to the Google quantum supremacy experiment on a single GPU. So there's been many research papers showing how you could do these on HPC instances. This is just on a single GPU. So let me get to quantum error mitigation. And this is actually a buzz term that has emerged from a broader ecosystem of research that spans from open quantum systems to, as mentioned earlier, quantum error correction, but also has to do with rational quantum algorithms in these devices, quantum optimal control, and quantum characterization, verification, and validation. So all these fields were well established well before quantum error mitigation emerged, in the past, I would say, 10 years or even less. And what is the core principle of quantum error mitigation? So it's not an active feedback as in quantum error correction, where you need to actually correct with the syndrome, and you need to have special properties of your system, and actually we don't have the current overhead doesn't allow to scale up things at the current state of quantum hardware noise. So what quantum error mitigation does, basically all the techniques can be thought in this way. Instead of having a quantum program that, as we said, we can imagine as a simple quantum circuit that is given to a backend and then gives a noisy result in terms of a bit string, what you do is you modify, you compile in different ways your quantum program, so you get the statistics of different quantum programs, you run it on your simulator or hardware that is noisy, you get some results that will be different in different ways, and then you use some extrapolation techniques to get a better result, a better estimation than if you run just a single quantum program. And right now there is many techniques in this sort of like field. I will focus on zero noise extrapolation and probabilistic error cancellation, and I cannot get too much into the details of all of these techniques. But maybe very briefly, zero noise extrapolation is based on pulse stretching. I will get into the detail of that in a minute. Probabilistic error cancellation, instead of working of a pulse stretching of a quantum circuit, is based on the reconstruction of a noisy quantum gates or a single quantum unit of a single unitaries. Learning-based methods such as Clifford data regression are based on the idea that given a hard quantum circuit, you can generate a set of less hard or completely Clifford quantum circuits which are efficiently simulable. You learn the noise on those quantum circuits, and then what you learned about correcting the noise, the effect of the noise on those quantum circuits, you apply as a prescription to your hard quantum circuit. And then there are some techniques that actually are sort of like older to some extent. Symmetry-based techniques, well, symmetry is at the basis of quantum error correction, And there are many quantum error mitigation techniques now that are based on this idea of symmetry, but don't require this active feedback. So basically, they just project your system in a symmetric state, assuming that the noiseless system doesn't have these errors. And then there is dynamical decoupling and randomized compiling, which are even simpler techniques compared to the other quantum error mitigation techniques, because basically they're just a different way of compiling your quantum circuit by adding some gates that modify the interaction of the system with the environment with respect to your system. And there's a growing amount of literature in this field, but you can find all the references in the MITIC project that I'm talking about in a minute. There's also 2 interesting reviews by Suguru Endo and collaborators, and by Zen Yukai. So let me get to the specifics of noise scaling in zero noise extrapolation. So we mentioned that the noiseless Hamiltonian evolution, type evolution, is not the full story. There is something else happening, and we can model it very simply as a noise operator, Pascal L, with a lambda prefactor that is an adimensional prefactor, which we'll put to 1 at the noise level of your system. And what happens is that if you stretch the coherent pulse that governs your Hamiltonian, you're subject to an effectively increased amount of errors due to a part of a term that you cannot control. And this actually gives you a worse result. So you're telling me, oh, we're trying to mitigate errors while we're getting things worse. But the reason why you would do that is that because of that sampling idea that guides these quantum error mitigation methods. So this is a plot with respect to this noise scale factor, where you stretch more and more your coherent pulse. And this is an expectation value of a dumb quantum circuit that gives you just 1 as a result. And you see that it goes lower and lower and lower, the value of expected value. And this allows you to actually do a simple extrapolation to the zero noise limit, which is the result equal to 1. So this has been shown in practice in a seminal paper by IBM Quantum, published in Nature, where they did this for 2 qubits. And as you see, maybe just focusing on the central block sphere, you see that actually the blue plots are the ones that are closer to the outside surface of a block sphere. So basically you're effectively projecting out of the block sphere closer to the surface, so to the noiseless part of your time evolution, your system. So when we were looking at zero noise extrapolation, we said, well, this is a very powerful technique, but actually most users don't have access to pulse stretching because they don't have a quantum computer in their lab, and they just have access to quantum computers from the cloud through sending gates. So we came up with a technique that we call unitary folding, which is based on effectively doing this pulse stretching at the gate level. And the way you do it, imagine that you have, again, the simple circuit of the beginning, a Hadamard and a C0. We can call that circuit with a unitary G. And with global folding, I'll explain in a minute what global means, but with this folding technique, you actually add the dagger of that unitary, and then the unitary again. And due to the properties of unitaries, G dagger G is equal to the identity. And conceptually, like from a logical point of view, the quantum circuit on the bottom is exactly the quantum circuit on the top, if you don't have noise. If you have noise acting, which is something you cannot control with these parameters, then the results at the bottom will give you something that is worse than the result at the top. And also let me explain what we mean with global folding. So global folding, you actually fold the full circuit, but then you could decide to fold specific parts of your quantum circuit. So you could focus on adding strategies where instead of sort of like you can see it here pictorially, instead of duplicating the full unitary, you select the single quantum gates or chunks of the quantum gates, and then you do the folding in that way. So there are many strategies. And not only there are different folding strategies, but there are also different inference strategies. So what I was showing before actually was an exponential fit. Here we call factories in this open source project called Mythic that I will tell you about the kind of extrapolation you can do. It's not only linear, it's also exponential. It has been first proposed with this Richardson polynomial. And you see that actually, depending on the device that you target, you may see that some exponential technique, extrapolation technique may work better than the other. And in some cases, we believe this is due to highlighting the fact that there is a non-Markovian noise on the machine, as we believe was happening in this Rigetti-Aspen device, where actually exponential fitting was giving a worse result than quadratic fitting. So I spoke about the different kind of folding, and together with folks at Johns Hopkins, we asked, does it really matter what kind of folding technique you apply? And to actually understand the variance of noise on unitary folding, what we did, we studied different noise spectra, so colored noise, and so what were the differences. So you see here in a simulator, noise scaled at different levels with different folding techniques. A tortorized approach, the pulse approach, the global and local folding. And when you have white noise, you actually see exactly the same results. When you start to have a color noise, actually you see that some folding methods are better than others. And specifically we saw that the one that was performing best next to the real pulse stretching was global folding. And why is that? Well, because in specific we were looking at some time correlated noise. We thought that it was a competition of the slow and fast dynamics of the noise and of the folding circuit. And to do this, the collaborators at Johns Hopkins, they sort of like designed this idea of a frequency spectrum connected to each quantum circuit. So even before adding end of the talk. Sorry, I have to okay. So and they were showing that in this case, with different level of noise scaling, you would actually stretch and modify the frequency properties, the fingerprint of your quantum circuit. So I cannot get into the details, but imagine that this is a way of looking at the frequency response of your quantum circuit. And when you do this folding, what happens is that you would like actually the fingerprint to be as similar as possible. And what you see here with the gate level tortorization and local unitary folding, you're actually modifying the frequency, pushing them to the lower and higher frequencies, and so something is happening to your system that you would not like to happen. And finally, with respect to the topic of folding, recently Andrea Mani and Vincent Russo at Unitary Fund put up this very nice paper on the archive, which actually is based on the concept of layer-wise folding. So what happens if you want to apply different folding scalars to different parts of your quantum circuit, so to different layers. And I think this is a very complementary work with respect to recently proposed noise-aware zero-noise extrapolation by other researchers. And what we're showing here that you see the unmitigated result going down as your quantum circuit becomes deeper and deeper. Again, the real value is 1. With Richardson extrapolation, which is the standard way of doing this folding, you see an improvement, but actually you see also a different sort of like slope when you apply this layer-wise Richardson extrapolation. So I was speaking about a software program, and this one I'm going to tell you a bit more about now. It's Mythic. And how Mythic works is actually a thin layer that the user can access to without changing the usual workflow. So imagine that you run your quantum programs with your platform of choice. Circ, Qiskit, Penlane. Recently we also integrated Kibo. You can execute on any backend because Meetic is backend agnostic. And thanks to the use of these different techniques, you actually generate many intermediate circuits and then get many extrapolation tools to extrapolate the noisy results. And what we're trying to do is also to combine these different methods to see the sum of the methods get something better than the single use of the techniques. These are the main modules of Meetic, where you can see that many error mitigation techniques have already been ported or even developed. And they include many of the techniques I spoke earlier. And also recently this classical shadows technique. And there's also other software you can use, of course, that is open source for quantum error mitigation. So, in terms of impact of what we do at Unitary Fund, we're not a proper academic institution. And what we like to track is, for example, how many folks can do research with Meetic, so with the tools that we develop. And this is a non-exclusive list of research that has been developed thanks to the use of Meetic, for example, for a lot of quantum simulation experiments, as in this example where Z2 theory was being simulated on a triangular plaquette and on an IBM quantum device, and you can see that actually the blue results were getting closer to the ideal results. So Meetic can be installed with pip install Meetic. You can find it on GitHub. We have a white paper in Quantum. It has now more than 120,000 downloads. And specifically, we have many examples and tutorials that help get started with it. So Meetic was first established thanks to support by the RQC funding by DOE. And now we're really glad that the National Science Foundation is helping grow its ecosystem. So when contributing a new feature to Meetic, you always start with a request for comment document, which is sort of like a design document where you put how you would like to, what you would like to add. Here is examples from the community of folks who added to Meetic. And then there's like some usual steps that go into that. The request for comment is discussed, it's then approved. A pull request is open on the project, and then the documentation is added, and the results are included in the next release on PyPy. So, for example, this is an example of some snapshots from a design document from Purva Thakur, a member of our community. Is also a Unitary Fund ambassador, thanks to all the work she's done on QTIP, Meetic, and Tokit and other projects. And she included the possibility to have some uniformly inserted identity layers as a way of folding in zero-noise extrapolation. And one of the recent updates in Meetic that I would like to focus on, which I think is also one of the issues of quantum error mitigation right now, is that, as you see, there's many techniques, and the way they perform is usually based on some heuristics, especially at this stage. So you don't know if you should apply probabilistic error cancellation, zero-noise extrapolation, or some other technique, and you don't know to begin with what parameters you should start. But that's why we started building around this idea of a calibrator, which takes a set of standard quantum circuits of which we know what is the result. For example, they get you back to the initial state. They can be randomized benchmarking circuits, mirror circuits, quantum volume circuits, GHZ circuits, many circuits. And you apply to those, for example, on a simulator on your actual machine, given error mitigation techniques with some parameters, and then you see which one performed best. And based on this calibration, which is a quantum error mitigation calibration, it's not a calibration of the device, you then apply your technique to the problem of interest. Okay, I will get a bit fast on this. We have many collaboration ongoing. Okay, let me mention this. I mentioned zero-noise extrapolation, and in a passage briefly, probabilistic error cancellation. But one way of looking at those techniques is that with zero noise extrapolation, you scale the noise factor, but you keep the quantum circuit the same, as you see in this plot on the left. In probabilistic error cancellation, what you do is actually you change the property of your quantum circuit, and you do it at a given noise scale level, because you actually change the gates, because you want to sample among different noisy gates to reconstruct the original gates. But if you look at this at the level of circuits, you can actually map it in this way. And so we propose a technique that actually is a noise extended probabilistic error cancellation, which actually bridges these two approaches into a wider parameter space that is actually unified. And the way to do it is actually your decomposition of ideal gate that you use in probabilistic error cancellation, where you have here this noisy gate. You add a circuit index and a noise scale factor index to your decomposition. This is called the sum of this is called the negativity, and then you can sample in this broader system. And the way to do it is very simple. In MIDIC, you can see here a very simple number of lines of code to represent, for example, each quantum gate in a greater and greater decomposition on also multiple scale factor. And we've shown that this approach makes your quantum error mitigation more robust against an error in the actual noise level. So you see that it's closer to the ideal value, the NEPEC plots that you see green compared to the other plots. So the further you move away to the zero level, you're actually moving further and further away to the actual noise level, and so compared to what you assumed. And so the fact that you get closer to the expectation value of 1 with an NEPEC approach means that it's more robust also to errors in estimating the noise. And that's just another way of looking at the differences in the extrapolation, where you have, on one hand, you have, well, this is just another technique that I cannot get into too many details about. But one thing I also want to say is that this approach also makes quantum error mitigation more convenient from an overhead perspective. So the quantum error mitigation compared to quantum error correction has the upshot that doesn't require more qubits, but the downside is that you need an exponentially large number of sampling in order to apply it at least in an unbiased way. And what we show with this hybrid NEPEC approach, as in the case of probabilistic error reduction, is that you actually don't extrapolate to exactly the zero noise value of a noise, which is a psi here in this case, but actually you do it to a lower level that has the advantage, sorry, I'll just go a bit quick here, has the advantage of, if you get to these points, of having a much lower overhead compared to the exactly the zero noise level. So this is the scaling of the sampling cost as the circuit depth grows for zero noise extrapolation. And in this hybrid approach, you actually reduce the noise. And actually to do this, we use two different approaches for the noise characterization. In one case, we use gate set tomography and an existing package called Pigsty. And in another case, we actually reduce the overhead also in the noise characterization using a technique actually proposed at IBM called polynoise tomography, which includes some noise correlation thanks to reduced Liouvillean space among the qubits. So you just have a smaller system. So I think I need to start to wrap up, kind of.
Yeah.
So let me just mention two things real quick. Quantum error mitigation is sometimes seen as quite different with respect to quantum error correction for the reasons I mentioned. So on one hand you have qubit overhead, on the other hand you have the sampling overhead. But actually the two approaches are starting to hybridize more and more, as you see from these proposed papers in the literature. And this is our proposal, which actually performs zero noise extrapolation at the logical qubit level. So you basically take, this is a surface code, so a quantum error correction code of growing size, and the take here is that you would like to scale to larger size, but due to the noise level, right now it's just impossible. So what you can do is that you can run smaller and then sort of like bigger levels of your quantum circuit, and you can extrapolate to a zero noise level. So we actually benchmarked this approach with respect to the naive folding approach of that system in terms of quantum gates, and we've seen, as you see, well, not in this plot, but we see that this improves the situation, and we also improve what happens with respect to the mitigated system. And we actually took the challenge, so it was a comment posted on Cyrate by someone, by a developer at Google, saying, why don't you scale it up to deeper circuits? We were doing just for deep, depth equals 100. And so we use a Steam, which is a compiler optimized for these quantum error correction codes, to actually scale the results up to 10,000 gates. And we've shown this improvement. Very brief comment, the fact that you actually split your large surface code into many smaller surface codes also helps you a bit in terms of qubit reuse. So you can imagine that it's sort of like virtual cores, they're not like real cores, but you can call these like virtual cores that then actually reduce quadratically, as you can see from the surface, the overhead when you run this sort of like statistics. We have to close. So let me skip this benchmarking of quantum error mitigation. Let me just mention these two slides, if I can. Okay. So as you see, not only in error mitigation, but in general, there is now many techniques, many metrics to benchmark quantum computers, and it's very hard to stay up to date. And frankly, it's just not possible to read all papers on the archive. So what we've done is that we got inspired by Papers with Code, which is a project in machine learning community that actually pairs articles with existing data sets of GitHub code and creates data sets to design metric, which here you see what happens for the quantum volume. Each of these data points, if you click on the platform, is actually an archive paper that gives you the result. And we've done it not only with actual results, but actually we started to track also where we had to respect to end use applications, such as finance application, factoring, cryptanalysis application, and so on and so forth. And here you see in this table actually where we are compared to where we need to be with respect to qubit number and logical operators, and you will notice that these are both two logarithmic scales. Okay, and finally, let me just get with this final comment. We're moving from software also to hardware. So what does it mean to have an open hardware project in quantum technology? Here you see two projects from the non-quantum world, Arduino and Raspberry Pi. And I'm really glad that we actually led a review paper on this project, which actually covers actually a quite rich ecosystem that already exists to design quantum processors, to then have a fabless approach with foundries that are open to startups or groups that have the possibility to grow these devices, to also packages such as the Quantum Instrumentation Control Kit that allow to control these quantum processors, for example, with fast FPGAs in the lab. And so it's a very rich ecosystem of which you can learn more in this review paper. And also glad to mention that there is this open quantum design effort at the University of Waterloo, which actually is a fully open source quantum computer from the ground. So all the design tools, all the software, but also the components are fully open source, and hopefully to be open to access globally in the near future. So I'm really sorry I kept you waiting. I know you came mainly for a pizza, but yeah, this is the last slide of the I'm joking. This is the last slide of the talk, and thank you very much. And if you want to be in touch, this is my email. Thank you very much.
Thank you very very much, Nathan, for this absolutely fascinating vision about the development of software for quantum and quantum for software. This is really fantastic. Yeah, I open the floor for questions or comments if you have any. Yes?
Hi, that was a great talk. I was really happy to see Quest in the simulator list at the very top right there.
Great.
What I was going to ask, one technical question, one not so technical. So the non-technical, you mentioned that the survey the Unitary Fund did showed that most people weren't using simulators because of poor documentation. Does the Unitary Fund offer funds for solely unsexy things, like making documentation for existing projects?
Definitely. So, I mean, the microgrants requirements are super open. So, usually the applications are reviewed by the advisory board, and if there is like enough impact to warrant a grant, that will be funded. So actually writing documentation, or even sometimes even writing small additions to existing projects is completely worth a microgrant. So if you have this idea, you should apply.
Absolutely.
I should also mention there is another program to which we're trying to get in, which is Google Season of Docs, which is designed to help projects write for documentation.
And the technical question, I didn't really understand why folding as a technique would help errors at all. Is that purely because it helps subsequent error extrapolation perform better, and for pulses specifically? Like if I have a silicon-based quantum computer where I'm controlling dots using gate voltages, I can't use folding there, right?
No, you can. So folding is applied at the level of the way we implemented in Mythic at the gate level. So by running a different quantum circuit, you can apply folding.
But isn't the physics of the benefit depending on the ultimate pulses?
It depends on the pulses, but also on the noise, which is what you don't control. And so to answer your question, the first part of the question, with folding, you make your quantum circuit longer, so you make things worse. But then you collect more data points in this sort of like quantum noise landscape that then helps you extrapolate to the zero noise.
Oh, okay, I see. So the effect is to change the noise characteristics rather than some pulse-specific effect.
Again, not really the characteristic, but the impact, the base level impact of a noise on the overall quantum circuit. And of course, the trick, as I said, there is a lot of heuristics, because you may already be starting with a level of noise that is so hard that if you make your system just longer, like deeper your quantum circuit, you just get things that don't help you extrapolate.
I see. Thank you.
Any other questions or comments? I actually have a couple of them. So the first one is quite obvious. In the PEC, is there any advantage, and can you see an advantage from assuming that noise is not just separable, but it's correlated over two or even many qubits?
So sorry, in PEC?
It means when you learn your noise, can you increase the accuracy of PEC by assuming that the noise is not fully so that there is correlated noise?
Yeah, absolutely. So that was that paper with Peter Orth.
Okay, and how far do you have to go? Because that also tells you something about the nature of the noise that is actually present in the platform you are studying, right?
So we did it only with simulation, and we did it, I believe, for 1 or 2 qubits.
Okay.
So we lowered the expectations. So in the paper by the IBM team, they used this correlation. They also applied to a couple of qubits.
Okay.
No, actually more than a couple of qubits. But yes, the reason why we implemented this NEPEC approach was to lower the overhead, because probabilistic organization is an unbiased estimator, but it's very expensive from the sampling point of view.
Okay.
And maybe to answer your question in another way, in a survey that we did without any characterization, which is this one I couldn't speak about. So we looked at different devices, IOQ, IBM Quantum, Rigetti, IBM Lima. So this is actually experimental data. You see that so if you get something above 1, which is the dark line, you see an improvement at different depths without any fine-tuning with respect to the specific noise. But what you see actually there, that PC, in both cases, for various circuits and RB circuits, is a one performing worse compared to synchronous extrapolation. And the reason is exactly that if you don't have a good noise characterization for PC, you don't get a real advantage. So here I was just assuming the polarizing noise.
Another question. I mean, in all this context, if you try to simulate or to learn a noisy channel, okay, so and that you want to use either for cancelling it, or if you are just simulating a normal quantum system. Since you assume that your quantum technology platform, you start from some pure state and you pile up mixedness, entropy, okay? Is there any advantage from assuming, at least in the simulations, that you have low rank, low entropy systems from the simulation point of view?
The comment about the quantum state.
If you want to simulate a quantum system that starts from pure state, the reasonable assumption is that it mixes up gradually, and so at least on a transient, it will have a low level of entropy, of fundamental entropy. Okay? So is there an advantage in simulating this system, assuming this feature?
I would say that you get this for free when you apply, for example, a Limblad simulation, right?
Yeah, but Limblad simulation needs to simulate the whole density matrix, whereas you
we haven't done it, frankly. So I need to think if the approximated technique that I showed with QREC is actually a non-physical approximate technique. So it's not like the noise you introduce is not really physical noise, but I think it has a correspondence to von Neumann entropy. So maybe it's something to look at.
Okay.
There is a technique doing rank compression of density matrices on the fly, which is pretty much exactly as you described. Exploiting that your density matrix can be rank compressed after each GPU hearing operation.
But you don't want to inflate it in the first place.
So if you start with a pure state, then you're already keeping it small, and then let a little bit of mixing come in as you go.
Interesting. Maybe we should look into that.
I will talk to you about that this later. Any other questions or comments? Doesn't seem to be the case in this case. Thank you very much again, Nathan, for this fantastic.